Hello, welcome back to another episode for Second Brain, AI powered business thinking. I'm your host, Vimal Patel from RoundTechSquare. And today we have a guest, Kean from Molecular U. It's a very unique company. We will find out more about it and then we'll ask those questions related to tech and AI to him. Jim, thank you very much for being over here. Welcome to Second Brain.
You bet, Vimal. This is an honor to be here, and hello to your audience.
Okay, wonderful. Thank you very much for here to be here at RoundTechSquare Second Brain. The question to you is that just let us give us some kind of an information what Molecular U does for the mankind.
Yeah, we're one of an emerging set of companies that is changing your health and clinical science and wellness from a reactive mode to a predictive mode. And it's really amazing science because it's literally looking at 288 biomarkers at your molecular level, but we're not single biomarker oriented. We take those and we'll form them into over 26 risk signatures as well as biological pathways. And what's important about that is that these are highly predictive. And in a lot of cases, you may feel or appear healthy, but the modern system doesn't pick those up unless they're super obvious. But in a lot of cases, things start going awry earlier than you think. And the good news is there's a lot of things you can do to influence the markers through lifestyle, diet, sleep, stress reduction, etc. So it's a pretty hopeful message, but it is going to be where medicine is going over the next 25 years is predictive versus reactive.
Okay, wow. So I think in our tech language or in our tech industry, we always talk about that, how can we be more proactive to a technology launch or to something to kind of solve the problem versus really know the problem and then fix it. So it's very nicely done in a health industry to do something like that is always take a lot of courage, expertise and experience. So yeah, so thank you very much for that. Now here is our question saying that in a Molecular U, what did you use? Are you using any technology, any kind of tools or softwares to make this wonderful medicine?
Yeah, there's a number that have gone into this, and there's a saying in science that every great scientist is standing on the shoulders of the great scientists that came before them. And so we're really a reflection, I'd say, of 30 years of discovery and advancement. And it started with the Human Genome Project. And a good way to think about your genome is you're blessed with that at conception, and those are like your architectural plans. So think of yourself as a complicated building, and you're made out of proteins and metabolites. So that plan, though, genes aren't that predictive; they're possibilities. So as you go through life, you're exposing your genome to the environmental forces outside of it. So that could be diet, that could be clean air or bad air, good water, bad water, stress, alcohol abuse or not, all these different things. And your body actually doesn't care because it's on a really specific schedule. It has to produce 25,000 proteins continuously. And it can either make really good ones or really bad ones. And so what happened is the genome was finished. And then two scientists, both in the metabolome and proteome, led to lesser fanfare the Worldwide Metabolome Project and its counterpart in the proteome. And that was about 10 years after that. And they start realizing that is the best data set your body can produce is what's going on with your proteins and what's going on with your metabolites. So then the next task became is how do you measure this? Because you want to have both very sensitivity, but it also has to be specific. And so there's instrumentation called PCR, machines polymerase chain reactions used extensively, a really great set of instrumentation, but that relies on amplifying. And the problem with amplifying, you can discover more targeted biomarkers, but they're not as accurate because you had to amplify them. And then how do you get sensitivity? Well, fortunately, there's a technology called mass spectrometry that allows you to both be sensitive, so measure really small quantities but at a very quantitative level. And so that's what was focused on about 14 years ago. And since then, a couple really highly placed scientists in the world have used that to measure these key data sets. And the cost is just like Moore's law. Costs have come down. Things have also, about every 3 years, they get incrementally more sensitive, so you can measure more and more things. And so we're right at the dawn of being able to measure a lot of things at a highly sensitive way. And because it's mass spec, it's super quantitative. And the comparison is between the old style of diagnostics, those are about 70% accurate on average. So with mass spec, because you're directly measure at the femtomolar range, you're routinely in the 90% plus accuracy range.
I see. Okay. So, I mean, thank you for taking to the journey of how the human body work and functions at the same time. All those calculation, all those analytics are so important for a medical, kind of a medical industry to understand about the human body to take the action. Now, obviously, you just mentioned a couple of instruments. Those instruments must be working as a hardware and a software combination, and then software does their part, hardware does, measuring part and stuff like that. Now, in this current scenario with your product, any complex AI modules or any complex AI studies or, under maybe research and development, are you using any AI tools or any kind of infrastructure of AI?
Yeah, there's both AI and machine learning. So what happens is you get all this beautiful data out of, say, so we take about a half a tube of blood. It's super
Okay.
efficient with material. And then we can simultaneously run 288 markers. So if you look at a conventional diagnostic, trying to do that, if you went to maybe one of the consumer diagnostic companies, to get that, they usually will draw 18 tubes of blood. So first of all,
Wow.
it's far more efficient. But then because they're drawing them separately, they have to send those tubes out to different labs. And so the data doesn't always correlate. So we're really good at multiplexing because we run all of those on one run from one tube of blood. Then when the data comes in, the difference between us and the old way of doing things is that the medical industry is very single biomarker oriented and they don't really trace out relationships with the other biomarkers. But when you think about it, that's not how biology works. Biology is everything's interconnected in your body. So if you will pull on one part, it influences other parts of the body. And it's the same thing at the molecular level with your biomarkers. And so the next thing we do is we assemble those markers into either biological pathways, which are the little sub engines of your body, like inflammatory reflex or blood clot mechanism. And so we do those for biological pathways, but we'll also assemble it into predictive risk signatures. So, for example, what is that? A great example of that's our Alzheimer's signature has 23 biomarkers. Because we're not single biomarker oriented, that it actually increases our accuracy. But then the computational aspect of that comes up is calculating the ratios and the rate of change in the algorithms of these really densely complex signatures gets very computationally intensive over time. The other interesting thing is that's only going to increase because if you think about it, the human map of the proteome metabolome is about 75,000 metabolites, so about 100,000. We're at 288, and we're the world's leader at multiplexing that many in a tube of blood. Our next version is going to have 1,000. So if you just think about it, we only are going to scratch the surface of 1%. And those are, again, not single biomarkers. They're all related with each other. So as you add that, grows order of magnitude complexity each time. When you get measured and your sample comes in, we actually then need to compare that to a master biological model with multiple signatures, not just like Alzheimer's or metabolic or cardiovascular or other forms of cognitive function or liver. You've got to basically cross correlate all those body systems with each other. So that gets computationally intensive as well because we're constantly, when we get, for example, a map of here's what a stage 1 pancreatic cancer looks like in one patient. The next time we see that pattern, which happens to be 53 biomarkers in a particular shape, machine learning, when the sample comes in, runs against our entire inventory of known heat maps.
Okay. Wow. Okay. So first of all, it was so fascinating to know saying that 288 biomarker, you are the world's leading company who have achieved that goal of one vial of blur and countering 288 biomarkers versus you just said 18 vial of blur to kind of, do it less than 280 or maybe like,
Yeah,
around
no,
that
it's
time,
it's
18
about,
versus one.
I won't say the company, but they measure about 150.
Wow. Okay. So half of the biomarkers, 18 vial, which is 18 times more, one vial, 288 biomarkers. So that itself is just, very, very crazy numbers in terms of results. Now, you nicely said saying that this machine learning, it becomes very important for you because, this many numbers and measurement of all those markers. It's important that the data is being calculated correctly with a lot of accuracy, and then you just put it out there for the medical experts in order to kind of diagnose this everything. So yeah, very nice. Now in that same question saying that if there is something which you think that okay, the AI can do better or AI can do more versus you are going in 288 biomarkers to 1,000 in down the line. So how smartly or how intense are you using the whole AI to kind of reach that target?
Yeah, so there's a numerous areas we need to use AI and different tools. So just starting from the top, so every single biomarker by itself, um, the way we decide to include it in our tube of blood or not is it has to be scientifically validated worldwide. And so think about this, there's about 1 million new pieces of validated scientific literature and studies published every single year. And that's stacked on all the prior years before. So specialized AIs need to search the entire compendia of studies. If we can find a biomarker is validated in at least 3 independent studies, then we'll deem it worthy of looking at as being associated with a particular condition or pathway. So we'll bring that in and then we'll see if we can replicate or reproduce the studies. And if we can, that makes it, then we include that in our next version of our panel. Okay, so that's one area. It's just combing all that literature, because otherwise we'd have to go whole cloth, put together a gigantic study, and we're a small company, so we'd like to piggyback on other work and just try to reproduce it, which is a lot easier. So that's number one. And it's a very specialized set of AI because it has to be trained on scientific literature
Okay. Okay,
and
nice.
very specific. So that's one. I'll pause there.
Yeah, okay. Okay, so thank you. So what I'm learning right now is that the industry like, Molecular U, where they are trying to do a lot of R&Ds in terms of doing things or helping medical industry very well to do with the accurate data, with a lot of machine learning, and then, provide something out there on the hand of doctors and then, medicine people, saying that with the use of AI and technology, this can do wonders. So now, if somebody is listening to this thing and then, I'm trying to understand, saying that what do I do, or what kind of a problem or what kind of a challenge which I can still work on to help this industry or to help the efforts like yourself, what you are doing for the medicine, that what do they understand and what do they think around the areas of saying that okay, hey, this the kind of technology if I create, this will be a help to this industry.
Yeah, so helping get a handle on all of the validated scientific literature and also sort which literature, like did they follow double-blinded study protocol? Because the biggest issue on science is can you reproduce it, right? So making sure it's high quality literature that gets surfaced. I'd say the second thing then that happens once we validate a marker is you run that, and then when you discover a unique pattern, like I mentioned, pancreatic cancer, we discovered the heat map for that in 2023, and that's a 53 biomarker pattern in a particular heat map shape, and those happen through machine learning, comparison, things like that. So that's another one. And then each specific marker that we include The doctors actually would like to, some are saying, okay, well, we want to know why you included this biomarker. So we actually like to group published studies, and it comes from they have a what's called a PubMed number. And so we always include the PubMed number in the biomarker description in our user experience. So any dedicated doctor wants to look it up or scientist, they can. And then we're starting to map that out to not only PubMed, but also like other databases like nutritional journals. Quite a bit of the of individual markers, the hopeful story is that you don't have to get medical treatment. Most of these markers you can optimize with diet and exercise first and supplements. It'd be nice to know, like this marker responds to fish oil. You know,
Okay.
yeah.
Okay. So
Still a lot of hallucinations too when
I
we
see.
search literature and match with markers. So we still have to do quite a bit of manual labor to make sure they're ultimately really good publications.
Wow. Okay. So there is a still a lot of vacuum or a lot of space in terms of R&D, in terms of like, working out for all these publications, providing them right data. So that teaches a lot. I mean, we are going towards the end of the podcast, but the whole journey of making us understand that, how complex medical science is in terms of, creating something out of the world and then use of AI and technology. And you guys are doing it. You have did it, and then you did not stop right there. You just keep going and then doing more and more. So thank you very much for doing that, Jim. If I may ask the last question, saying that if somebody wanted to know more about you, about the brand, where they can get tasted, and then where they should come or where they can find you at.
Yeah, so our website's www.molecularu.com. And then, because I'm super appreciative of your audience and whatnot, I'd love to give you a link to a friends and family discount link
Wow.
where if
Okay.
you're interested, you can order the test and
Yeah,
see what your
sure.
biology's doing and even book a session with a scientist to tell you how you work.
Wow. Okay. I can't wait to do that. I will definitely do it for myself at the same time. Thank you very much to be very generous and then give us that link for the audience who can order the test. But till right now, we'll take a pause and thank you very much, Jim, to take us to the journey of the product and then technology and then teach us that there is still a hope. There's still a lot of vacuum where we as a tech people can come in, do something about it, work with you guys, and then just kind of help you to create some piece of technology to help you to do your research and then
Yeah,
and
I
then
appreciate all
produce
the
something.
efforts of you and your and your audience, data scientists and computational people. So we need all the talent we can get.
Thank you very much, Jim. Till then, thank you very much. Have a nice day, and see you next episode.
Bye bye.